The cold dark matter paradigm provides a highly accurate blueprint for the macroscopic universe. It maps the invisible scaffolding that forms the cosmic web. Yet, when we shift focus from massive galaxy clusters down to individual dwarf galaxies, that predictive power breaks down. Computer simulations built entirely on cold dark matter expect steep, dense central cusps and hundreds of surrounding satellite halos. Telescope observations consistently reveal shallow galactic cores and a fraction of the expected satellites. For over 3 decades, the consensus approach to reconciling these scales has been the search for weakly interacting massive particles, or WIMPs. To find them, physicists constructed immense experimental apparatuses, colliding protons at nearly the speed of light to force interactions with the visible spectrum. Simultaneously, multi-ton liquid xenon vats like Xenon NT and LZ were buried deep underground to shield them from cosmic rays, waiting for a single WIMP to strike an atomic nucleus. The result from these arrays has been absolute silence. These exhaustive null results have systematically excluded the canonical parameter space for WIMPs. A continuous failure to detect subatomic particles forces a strict reevaluation. To resolve the structural anomalies within individual galaxies, astrophysics must explore macroscopic dynamics rather than microscopic particle collisions. This requirement led to the Phase-Transitioned Stringy Dark Matter model, a framework born from a structured adversarial dialogue between speculative inquiry and formal physics. The initial hypothesis began with a provocative analogy. Could dark matter act like a non-Newtonian fluid, remaining fluid in space but solidified under dynamic pressures? The mathematical constraint on that analogy is severe. Observational data dictates that dark matter must act as a collisionless fluid. Its constituent parts interact almost exclusively through gravity, not friction or kinetic impact. The synthesis between these two positions required a mechanism that creates rigid structures without violating the collisionless constraint. The solution is a local, density-triggered phase transition. Under the PTSDM model, dark matter begins as an ultra-heavy scalar field. Then, at a specific density threshold, it undergoes spontaneous symmetry breaking, transforming into a localized network of oscillating cosmic strings. By treating dark matter this way, the model explains galactic structures entirely through the macroscopic physical dynamics of massive string networks, bypassing the unobserved subatomic particle entirely. This graph illustrates the symmetron potential field equation, dictating dark matter's state in the early universe. From the Big Bang through redshift 20, dark matter rests safely in the symmetric minimum of this curve, existing as an ultra-heavy scalar field. Crucially, this field possesses zero coupling to the standard model of particle physics. It generates mass and bends spacetime, but it is completely insulated from electromagnetic and nuclear forces. Because of its heavy mass and lack of interactions, this scalar field acts exactly like standard cold dark matter. It generates the deep gravitational wells required to pull primordial gas together, perfectly reproducing the large-scale cosmic structures we observe in the cosmic microwave background. The model establishes its baseline validity here. It preserves every confirmed success of standard cosmology in the early universe, restricting its novel physical behaviors until space expands further. The mathematical trigger for those new behaviors is embedded directly in the symmetrotron field, which is intimately coupled to local dark matter density. As the universe ages and expands, the overall ambient density of dark matter drops. Eventually, the density within individual galactic halos falls below a specific critical threshold. When that threshold is crossed, the local mathematics invert. The symmetry breaks. The field rolls from a zero state into a new energetic minimum, releasing massive amounts of stored potential energy. This surge of potential energy crystallizes directly into macroscopic topological defects, one-dimensional faults in spacetime known as cosmic strings. These newly formed strings operate with an exact dimensionless tension value of 10 to the negative 11. Because the transition is strictly governed by local density drops, the cosmic strings only form inside the confines of expanding galactic halos. The dark matter converts locally, completely eliminating the need for universe-wide particle interactions. This local transformation addresses the structural anomalies found in dwarf galaxies, starting with the cusp-core problem. Standard physics predicts that dark matter collapses into sharp, ultra-dense spikes at the center of these galaxies, yet observations show flat, evenly distributed cores. Competing hypotheses, like fuzzy dark matter, attempt explaining these flat cores by introducing hypothetical ultralight bosons, relying on highly speculative quantum pressure to resist gravity. The PTSDM model relies entirely on classical mechanics. The cosmic strings formed during the phase transition are trapped within the galactic halo, oscillating continuously at relativistic velocities. This diagram compares the differing models. While standard matter collapses in Model A, the rapid physical whipping motion of the confined strings in Model C generates a massive outward kinetic pressure. Calculating the typical velocity and energy density of a string network within a 1 kiloparsec halo yields an oscillatory pressure of roughly 10 to the negative 4 ergs per cubic centimeter. That exact figure matches the inward gravitational pull of a typical dwarf galaxy. The physics balance naturally. The macroscopic kinetic energy of the string network holds the dark matter outward, creating the observed flat cores without requiring new quantum forces or complex feedback loops from baryonic matter. A theoretical solution for galactic structures is only valuable if it generates falsifiable predictions. The recent detection of a stochastic gravitational wave background provides the testing ground for this model. This chart plots gravitational wave frequency against amplitude. Standard cosmic string theories postulate that strings formed fractions of a second after the Big Bang, producing the smooth, flat power law spectrum seen here. PTSDM predicts a stark contrast. Because its strings are confined strictly inside individual halos, their physical lengths are limited. This limitation forces their gravitational waves into a concentrated range, resulting in a sharply spiked resonant peak in the nanohertz band. That exact nanohertz frequency range is actively being monitored by international networks of radio telescopes and pulsar timing arrays. If observatories map a sharply peaked spectrum rather than a smooth curve, they isolate the definitive signature required to distinguish PTSDM from all WIMP and standard string theories. The framework yields a second direct prediction: gravitational lensing scintillation. The relativistic oscillation of massive strings inside dwarf galaxies bends spacetime dynamically, causing background light from distant quasars to violently flicker. This deflection is on a micro-arcsecond scale, an effect perfectly suited for detection by next-generation instruments like the James Webb Space Telescope. The third falsifiable metric is the void gravitational wave anticorrelation. The core mechanism of the phase transition strictly requires dark matter density to drop below a local threshold inside a halo. Consequently, the massive empty cosmic voids between galaxy clusters, which lack that initial concentrated mass, will never trigger string formation. Any large-scale survey mapping the gravitational wave background must show a strict absence of emissions overlapping with these cosmic voids. Confirming that precise negative space in the data validates the density-triggered mechanism. A theoretical exercise comparing dark matter to impact solidifying fluids was subjected to rigorous mathematical constraints. The result is a coherent, testable framework that solves galactic structure problems without relying on invisible subatomic particles. Dark matter operates as a dynamic, localized network of cosmic strings, actively ringing across the universe at frequencies we are just now learning to detect. If you like this video, like and subscribe. This was created by Synestex Systems LLC, which was founded by Shane Persinger.